in DC we have polarity. And there are two ways of switching DC electronically. And one's called syncing and the other's called sourcing. And the reason there's two different kinds is that originally they couldn't build a transistor that was sourcing. They could only build a transistor that was syncing. In other words, it would take a voltage and pull it down to ground. And that was transistors. And those were NPN transistors. And we didn't get PNP transistors for a long time. And as a result, there's a lot of sensors out there that are NPN and not as many in PNP because they came along later. And so it was real common to see NPN stuff. So we're not using the like automotive colors for the wires, which would be black and red, which is what you see in your car, where the black is the negative and the red is the positive. Instead, we're using the European standard, which is the blue wires are the common, are the negative 24, and the brown wires are the positive 24. And the reason I say that the blue is not common and the red and the brown is not common is because depending on whether you're working with PNP or NPN changes what you would consider the common. Okay, so in our case, all of our fuses and power is the fuses are all on the plus side. Okay, whether the device is NPN or PNP, all the fusing is done on the plus side. And that's just by convention. It's not an absolute rule that, but typically what you're going to find is that the plus is always the fuse side. Now, another thing is, simple thing, but the fuse holders we're using, they pull out like this, all right? So the top is always the line side. In other words, power comes to the fuse always at the top of all the devices here, except when they went to VFDs and they put everything on the bottom. but these two VFDs, they have it on the top and to the bottom, and contactors are always on top to the bottom. But then they went to bigger VFDs and they put everything on the bottom. And it's actually a pain in the ass because it means you have to loop the wires around the thing. Whereas it's really easy when it's just like these two here are coming right off the breaker right here, and I don't have to go all the way out around and come back up. Why they did that, I have no idea, but that's the way VFDs are in the world. So anyway, the point about the fuses is that you want the fuse to fall down out of the connection. So when I see a fuse holder where it's flipped the other way, that's no good. And we always have there's always a master fuse. In other words, you come off this transformer and you want to protect the transformer from overload. Okay, so you use a fuse in the hot wire that is sized to handle the load that the transformer can safely handle. All right, so we come out of there and we come down and we go through a fuse. Now we go in the top of that fuse. And then we come out the bottom, right? Because it's always fed top to bottom. And we loop around and we come up and we have jumpers going across to 4 more fuses. All right? So the first fuse protects the transformer. And the rest of the fuses protect the loads that are connected to it. Now, just like in your house panel, if you add up all the circuit breakers in your house panel, you might have 300 amps worth of breakers. But the main breakers say 100, right? And that's because the main breaker protects the cable coming into your house, and the other breakers protect the wires within the house, right? So that's why it's done that way. So we're doing the exact same thing here. We have like essentially a small power panel. We have one breaker, that's the main, that protects the transformer and the wires from that. And then we have 4 more that go out to the sub-circuits. And in the case of DC, we have exactly the same situation. We have the plus and minus coming off of a DC power supply, and this brown wire goes to a first fuse and then jumps to all the rest of the fuses. All right, same thing, in the top of the first fuse, and then loops through, comes back up around and feeds the top of all the fuses, so the loads are always on the bottom. So as a consequence, when you're troubleshooting, if you're trying to find out if there's power, you always check at the top of the fuse first, because that'll be the feed side. If you have power there, then check the other side of the fuse, right? So that's how that comes into play, is that you know that the top. Now, if you don't find power at the top, well, then it's not the fuse feeding the thing that's causing the problem. It's up further, right? So, so the AC and the DC, the protection with the fuses and stuff works exactly the same way. And so down here we have small fuse holders that are that handle a smaller fuse. Now we use these little tiny fuses, of the 5x20s. I use them on the DC circuits. That again is not an absolute requirement. I could use the larger 1/4 inch and 1/4, but the reason for the difference is I like that when you pull up on a fuse, you know you're looking at DC versus AC just by the fuse size. And the other side of it is that fuses have what's called interrupting capacity. In other words, they're rated for their ability to break a amount of current without exploding and blowing up and damaging the equipment, okay? And glass fuses in particular, the reason they're glass is because there's something you can learn about a failure by the fuse, all right? If I pull a fuse out and, I can see the element, I know that fuse is good, right? But let's say I pulled it out and I couldn't see the element, right? It was like gone, all right? But the tube was still clear. What does that mean?
It took a current and...
It means it was an overload. In other words, the current was more than the fuse was rated to handle, all right? However, if I pulled that same fuse out...
And it's black.
What does that mean? That means...
Rob wired it.
It means that there was a high voltage, a high current surge. It vaporized the thing because it was a real high current. And so you can tell just by that what kind of problem you're looking for when you find a bad fuse. If I see it melted out, I'm not going to find a wire. If I see where it's just gone, I'm not going to find some place where it arced. That's or that kind of thing. That's like the equipment that it's feeding went bad. And is pulling too much current. That kind of thing. Now, if I see it all blackened, I'm going to go looking for a pinched wire or that kind of problem. I'm looking for something that was a short to ground or to the other side and caused it to flash. Okay, now years ago, in what fuses can tell you, there was a car wash, and the guy had burned out 5 big blowers in a row, and his electrician couldn't find the trouble, so he asked me to come in and check. And he had a pile of fuses laying there, and we looked at everything, and I couldn't find anything wrong. And I see this pile of fuses, and I pick them up, and I said, "Did it blow all the fuses each time the motor went bad?" "Oh yeah. "Oh, I think I know what's wrong." And he's like, "You reading tea leaves?" I said, "Well, kinda." He said, "You see, I have 12 fuses here, and there's 3 fuses on each motor. And you notice that 4 of them are slightly blue on one end. They were big copper fuses, right?" I said, "The motor didn't go bad. The fuse blew the motor." He said, "What do you mean?" I said, "Well, they turn blue like that when they get hot. Copper turns blue." I said, "So one end of that fuse was getting hot." So we opened up the main switch, and sure enough, the fuse block was all burned up. So what was happening was his motors were being burned out by the fuse blowing and single phasing the motor, and then the motor would trip. And in the case of a car wash, motors have what's called service duty factor, right? And three-phase motors have incredible overload capability. This is why your Tesla can accelerate like a rocket. It's because the motor in a Tesla might only be 100, 120 horsepower. But a 120 horsepower three-phase motor can put out over 600 horsepower for short periods of time. What's a short period of time? Well, in the case of a Tesla, it's getting to 65
seconds.
in 2 seconds flat. That's nothing, right? That's trivial. I mean, in industry, three-phase motors can be overloaded for a minute or two, without a problem, as long as it's not, continuous. In the case of the car washes, the blowers at the very end, they have really big blowers on undersized motors, and they use the service factor rating, and they actually overload the motor because it only runs for 30 seconds drying your car. But when you trip one fuse, the motor has no chance because it's overloaded already, and so it would burn the motor out. Right. So you can learn a lot by the fuses. Now, the fuses, these are glass. Then they have ceramic fuses. And the ceramic fuses, the difference is that the ceramic can take more heat and more, and hold in more force, And in big fuses, big power fuses, the elements inside are typically pure silver, which is why the fuses are so damned expensive. The power fuses, because they're actually silver. And what they do is they use a whole bunch of little tiny links all sharing the load. And that's how they get the high current capacity, but also the ability to blow really fast. So, and then they're embedded in sand. There's a silica sand inside the fuse to absorb the arc.